Any ideas, suggestions? The problem is this one. This is what we seem to obtain for the electric field at the point r plus r prime due to the charges outside. And the problem that I'm having with this expression is that at least if you look at the first term, there is no r prime dependence, so it is just basically 0. The expansion. Well, let's check the expansion. You see, if you just follow the steps that we obtain, that we allowed us to reach this expression, well, this one, we are looking at the electric field r plus r prime. Again, I repeat, r is the center of our volume v prime. R prime is the position at which we are evaluating the electric field relative to the point r. This was, in general, we can always write it in this form, rho of r double prime plus r multiplied by r double prime plus r minus r prime plus r divided by r double prime plus r minus r prime plus r. So basically what we are doing here is that r double prime is again the position of the charges relative to the origin of my sphere. So this is the electric field. Now we can of course just r's cancel in this electric field as it should. So this just becomes d cubed r double prime rho of r double prime plus r double prime minus r prime divided by r double prime minus r prime cubed. And now we said that, okay, this r double prime minus r prime divided by r double prime minus r prime is actually minus the gradient of 1 over r double prime minus r prime, the gradient with respect to, let's say, r prime. So the electric field created at the point r plus r prime, due to the charges outside my volume, is minus the gradient with respect to r prime of d cubed r double prime rho of r plus r double prime divided by r prime minus r double prime. So basic.
Shouldn't the gradient of the potential at r, so it should be the gradient with respect to r at r prime.
Well, you see, r is just a constant vector. Because we are considering, you see, the volume is constant. We take a point in our volume. We have to take the gradient relative to that point. We are calculating the electric field at this point. So we have to take the gradient with respect to the position of that point.
Which is the point of observation?
The point of observation, which is r prime, or r plus r prime. So we have to take the gradient with respect to r plus r prime. But in this gradient, we are only changing r prime because, as I said, r is a constant vector. So that is why we have the gradient with respect to r prime. Now the charge density at r plus r double prime, well, r plus r double prime is basically the position of the charges relative to my origin. And r prime minus r double prime is nothing but the relative distance between the position of my charge and my observation point. So this expression is correct. Now the next thing we do is r prime is close to the center of my volume. So r prime is basically less than the radius of my sphere. And r double prime is outside my volume, so relative to the is a point outside my volume relative, so R double prime is the position relative to the center of my volume, so R double prime is larger than R. So R prime over, R double prime is less than 1. And typically much less than 1. So what we do is we have this 1 over, or let's say R prime minus R double prime to the power minus 1/2. This is what we need. And this is equal to, no, not minus 1/2, minus 1. This is R prime minus R double prime squared to the power minus 1/2. If I take the square, it is R prime squared plus R double prime squared minus twice R prime scalar product with R double prime to the power minus 1/2. R double prime is the larger one. I take it out, R double prime, 1 over R double prime. What is left is 1 plus R prime over R double prime squared minus twice R prime scalar product with R double prime divided by R double prime squared to the power minus 1/2. The second and the third terms are small, so we can do the Taylor expansion. This is 1 over R double prime times 1 plus minus 1/2 of minus twice R prime dot R double prime divided by R double prime squared plus terms of the order of R prime over R double prime squared. And this leaves me with a 1 over R double prime plus R prime dot R double prime divided by R double prime cube. And my problem was this. I need to take I'm evaluating the potential basically at the point R prime plus R double, no, at the point R prime. And I was saying that, well, I want this to be, in terms of a multiple expansion, I'm doing a multiple expansion. This should be phi 0 due to the monopoles outside my volume, plus phi 1, again due to the monopoles outside my volume, but instead what I obtain is, this is what I wanted to have. I obtain phi 0 at the point R plus phi 1 at the point R prime. This is kind of what I didn't like.
I suggested that maybe the magnitude should not change with small changes, like the gradient. And so I decided that phi 1 that should be 0 to that, right? But maybe
Now phi 1 is not 0.
it's varying with respect to all phi.
Well, if it is 0, then we don't have any electric field. That's also not what we want. We want the average electric field, which we hope is non-zero.
I'm saying that the gradient of phi 1 will not be 0 because of the direction.
Okay.
So the magnitude of the electric field due to the dipole will not be affected, but the direction will change.
Oh.
Whereas in the case for the monopole, the magnitude will not be affected because we are assuming we are very far away. Right? But the direction is the same. So at the change of the position,
Well, let's give it a try. Does it make sense, I mean, this result? Or can we kind of make a sense out of it? So you see, up to this point, we started with the electric field outside. So this expression is true whatever the charge density is. I mean, we don't need to have a continuous medium. Whatever our charge density is, this electric field outside is correct. So let's just assume a point charge. Let's check. Rho of R is equal to Dirac delta R minus, let's say, R0. And if you just pick this expression, which we said is correct, it should be correct. So this is equal to d cubed r double prime. Rho is q r plus r double prime minus r0. R double prime minus r prime divided by r double prime minus r prime cube. And this is equal to, well, the Dirac delta just tells me that wherever I see r double prime, I should put r0 minus r. So it is equal to q times r0 minus r double prime divided by r0 minus r double prime. No, r prime. This is equal to q times, let's say, minus q times r plus r prime minus r0 divided by r plus r prime minus r0. Cube. So first of all, does this make sense? So this is our volume. This is our, let's say, r0 point. This is r. Let's say this is our r0. So r plus r prime minus r0 vector is this vector over here. So this is the vector r plus r prime minus r0. Well, it is almost correct, but the minus sign is wrong. The electric field at the point r prime due to the charge at the point r0 should be in the direction of r plus r prime minus r0, not the other way around. So that is one mistake we had. So let's go back. So this is r prime minus r double prime. First the observation point minus the position of the charge. So that is one mistake we had. If we correct it, now at least the electric field expression is correct. Okay, so at least this step is, at least for the simple case, this step is correct. Now let's look at the other problem. What is okay, let me, here we had the expression. This is the phi. Phi at the point r plus r prime, this is equal to this one. And again, rho of r is equal to q times the three-dimensional Dirac delta r minus r0. So let's write the potential. Phi at the point r plus r prime This is equal to, well, rho at r plus r double prime is equal to q times the Dirac delta cubed r plus r double prime minus r0. So basically, again, in r double prime integral, it just tells me that instead of r double prime, I should put r0 minus r. So this is equal to q over r0 minus r plus q times r0 minus r dot r prime divided by r0 minus r cube. This is the potential. This is the potential at the point R, as we said. Plus, well, this is the dipole of the external point charge relative to the origin. Right? Why? Relative to the origin of my volume. So it is non-zero. That also tells me where our mistake is, by the way. So that is where the mistake will come from. Okay, now we have to go. I mean, did you see the mistake? I mean, you see, we have this charge over there. We should be looking at its dipole moment relative to its own center. I just want to say a dipole over here. I mean, I don't really care whether I have whether it has a dipole relative to this point or in the center of V prime. That is not what I care about. So basically, think about this. I have an atom over there. Okay, so it will have a dipole relative to its own center, not relative to this point over here. I'm looking at the field over here created by a dipole over there. I'm not interested in its dipole moment relative to this point. I would rather express everything locally. All the multiple moments I would rather express in terms of its own relative to its own center.
Okay. The electric field due to this dipole takes into account the charge itself, the monopole, as if we had it at the center of the atom. Right?
You see, that is what we need. I mean, when we are talking about the potential, let's say at the point R, due to a dipole over there, which might even have its own charge, what I would like to write this as Q over R, due to its charge, plus P dot R over R cube. P is its dipole relative to its own origin or whatever.
But if we don't, it still have, or work is still correct.
It's still correct, no problem. But that's not what we are interested in.
Okay, so then how do we shift the dipole between one center and another?
We have already done it. This one. You see what we had done. So what we were looking at. This is our volume V prime. Okay. I have some charge distribution outside. Where is charge densities? Okay. Now I can just consider some very small volume. Delta V. It will have some charge Q, some dipole moment P, even higher multiples. So now we are basically reverting the problem. I have a localized charge distribution over there. What is the potential that it creates at this point? You see, if you remember our discussion in the multipoles, what we did there was we assumed that our charge distribution was at the center, and we were looking at the potential it created far away. So that, and in that description, we had said that if we have, let's say, a localized charge distribution, phi was the monopole Q over R plus the dipole. Plus higher multipoles. This was the result of the previous chapter. Again, this R is the, so you see here this volume V, let's say, has this dipole moment P, and this is the R vector. Do you remember this expression? Well, basically, the derivation is exactly like this, but you have to kind of change your perspective that it's not the charge distribution is not the one that is far away. The charge distribution is at the origin. It's the observation point that is far away. We will. Next. Now we will choose. I mean, you see, here what we have done. We have this delta V, some volume over here. So we said that if a system has a total charge, then this dipole moment depends on where you choose your center. Okay, that was kind of a problematic thing. That's something we have to take into account. But what we do is we have this delta V. We define all the multiple moments relative to some point in this delta V. Then P, we have the dipole moment relative to that origin. The charge, well, that doesn't depend on the origin. So in terms of this electric dipole moment and this R, the potential created at some far away point is given by this expression. So if we change delta V, of course, the origin with respect to which we are calculating these dipole moments should also change. But we kind of, for each delta V, I mean, we will treat this dipole moment of this total dipole moment of this volume as a property of the system. So different points will have different dipole moments. It will also be proportional to the volume. So we will basically define the dipole moment density by dividing this volume. So, and delta V will be small. If we take delta V to be very small, just changing the point will not really make too much of a difference, as long as you are within your volume to define this dipole moment. So the origins are kind of getting confused. I mean, we have this matter. We have some arbitrary coordinate axis. You can always choose it. There's one origin over there. Secondly, we are looking at this small volume around the point R, and we will be averaging the electric field over this volume V, which we assume is sphere. Now, then we have this other charges over here, which create some potential over here. So we have a localized charge distribution over there. So to describe the multiple moments of this localized charge distribution, we would better go to a reference frame, choose an origin that is inside this charge distribution, and then you define the dipole moment, the quadrupole moment, etc. And in terms of these dipole moments, the potential created at a faraway point is given by this expression. And this R over here is the distance between your observation point and the origin that you have chosen in your charge distribution. Okay. If the volume is small, well, R doesn't really change over the volume. It's more or less constant. Well, of course, we have many volumes, not just one. So we have the potential created at the point r plus r prime is actually 1 due to the charge density, d cubed r double prime rho of r plus r double prime divided by r prime minus r double prime. I'm not expanding this. Plus, there is also some dipole density. D cubed r double prime, let's say p dot r double prime minus, no, r prime minus r double prime divided by r prime minus r double prime cube. This is how I define the dipole density at the point r double prime. I just assume a very small volume over there, calculate the dipole moment, divide by the volume. And here, this P is the dipole moment density at the point r double prime. Aren't we? Why?
Because if some volume charges and the potential at one point,
Okay.
and then when you go back at one point again, some volume charges and the potential will be back one.
Well, that is this rho is rho out. So basically, we are this r double prime is integral is due to the charges outside my volume V, whereas r is inside my volume V. I don't see the double counting. That was also one of the reasons why we separated the regions outside and inside.
Now here, in this formulation, our center or origin is at r plus r prime, right?
The origin center of V prime is at R. We are looking at the potential at the point R plus R prime.
Rho is a function of.
The argument of rho, I'm always assuming that the argument of rho is the position of the point relative to the origin. R double prime is relative to the center of V prime. So to write it relative to the origin, I have to add the position of the volume relative to my origin. So that's why I keep on writing rho R plus R double prime. So this is basically, no. Let's go back. These are my conventions. This point over here is R plus R double prime. So the charge density at that point I denoted by rho R plus R double prime.
And dipole?
The dipole density at that point is also R plus R double prime. You're right, I have to write R plus R double prime over there. The origin for calculating the multiple moments. You see, look at the density. Now, basically what I'm actually doing here is, this is how I define the dipole moment density. So it is basically, I assume a small volume around the point R plus R double prime, a small volume of volume delta V. I take the point r plus r double prime as the origin, calculate the total dipole moment within this delta V relative to that origin, and divide by delta V, and then eventually take the limit as delta V goes to 0. So that is how I define the dipole density at the point r plus r double prime. So basically I'm specifying which origin I should choose. To the origin, of course, the origin to calculate the local dipole moment density. Not the origin of my coordinate axis.
This is equivalent to the previous discussion, where we considered the dipole with respect to
This expression, you mean? I adopt their equivalent because in this expansion we are ignoring terms that are really large. You see, if you take all the terms in your expansion, infinitely many of them, both in this expansion over here, which we did previously, which we thought it was weird, and also in this expansion, if you take all of the terms, they are equivalent. We are basically talking about the same property, same quantity, just expanding it in different ways. We are considering different Taylor, in a sense we are basically Taylor expanding with respect to different parameters. So they will look different. If you just take just one or two terms, they might be completely different. But if you take all of them, they are equivalent.
If you take the all volumes of the which is created the potential at one point, how will you define the I?
Now, can you repeat?
If we take the all volumes, which is one of them is I prime and plus I double prime, it will change.
Sure. And if, as you say, r prime is fixed, we are looking at the potential at the point r plus r prime. So that we choose that point first. Then we say that, okay, to that potential there are many contributions from many different patches which are located at r double prime relative to the center of my volume v prime. And I have to sum them all up. Of course, their contributions will be different. But is it possible that r double prime is equal to r prime? That seems to be one problematic region. Well, the boundary terms, we are kind of ignoring their contribution. Because they compared to all of the volume, they will just give a very small contribution. So r prime is never equal to r double prime because r prime is inside my volume. R double prime is outside my volume. So they are never equal. R prime is constant. R double prime is constantly changing over all my matter. It's never constant. But R double prime is never inside my volume V prime. Okay, so our time is up. So we will continue on Wednesday. Now the basic trick will be, okay, now we identify what is the potential created inside my volume V prime due to the charges outside my volume. So by just taking the gradient with respect to R, we can also calculate the electric field. Now with respect to R prime, we can obtain the electric field. Then we can average the electric field, or in fact, we can even average the potential. That's also equivalent. We will discuss it. Then these are due to the outside electric field. Then it will be kind of funny. You see, we had shown that this inside P. But if you remember, in a couple of days ago, we also showed that so I say in these volumes, we are ignoring the region inside. But this final integral just tells me that we can just add it. We can write this P as an integral over my volume. Okay, we will continue on Wednesday. Probably there's somebody waiting outside.